All right, thanks. So I anticipated last time the problem that we're going to solve. There's not going to be any theory today, which will be a case where there are reference frames that translate and rotate with respect to each other. But before we do that, I would like to see if any of you, I know that a couple of you have tried to solve this other problem I gave you, which was basically, I'm trying to remember how I've done this in the drawing, a modification of something we've done in class, I believe, right? So there were, say that I have a point up here, P, two bars, uniform slender bars. Okay, let's see. Let's call these, we call this the ground. This point down here, let's call it Q. This point here, we called it O. So I think we've seen in class something along the lines of just rotation of this arm about point O, and we call that angle theta. And then I invited you to try and solve the case where now this second bar, OP, is mounted on a vertical shaft, and this shaft is also rotating of an angle phi about the vertical direction, if you want to call this the vertical direction. So have you tried to solve this? I know two of you have come to office hours and they showed me what they've done. I don't want to solve it all the way. I think we should go through the definition of the reference frames and coordinate systems, which again, it's setting up the problem. If you do that right, then the rest should be easy. If you don't do that right, then you're in trouble. So, yes?
Did you tend for P to translate along that tube? Or just
No. Yeah. So I have rectangles here, but they don't really need to be rectangles. They can be just lines. So you can remove these rectangles with lines if you like. So there's one point here, one point QO, one line QO, rigid bar, and then OP. And I really care about finding the velocity of P as seen by an observer fixed to the ground, and acceleration of P seen by an observer fixed to the ground. I think those were the questions, right? Yeah. So this is a case where you have two rotations. And it's a little tricky to visualize the geometry. And again, in kinematics, we do geometry of motion. So the tricky part is visualizing the problem and breaking it into reference frames and coordinate systems. Once you've done that, the rest should be just writing vectors in the appropriate coordinate systems and applying the transport theorem. It shouldn't be much harder than that. So one comment I want to make about office hours, though. I got an email. Someone was concerned about me giving out additional information during office hours. I don't teach more theory or do additional problems. If you come to office hours, you ask me questions, and I of course help you with the problems. But if you don't solve any problems and you're fine, you're understanding everything, you probably don't need to come to office hours. That is not usually the case, though. So I'm not saying that I need to see every one of you, otherwise you'll fail. That's not the point. I'm just saying that those hours are for you to come and ask questions. So of course, if you're solving thousands of problems and you come and ask questions and that benefits you, you will be probably in better shape than someone else who is solving no problems and never showing up at office hours. Those are the two extreme cases. But again, I'm not going to give more information or any secrets during office hours. They're just there for you to be used if you're really solving the problems and you have questions. If you solve the problems, you understand everything, you don't have questions, good for you. Okay? So let's just understand what it is that we're looking at here. And I don't want to do the entire calculation because I really want to do the other problem. At least try to finish it. I have how many rotations? Two rotations. How many reference frames do you think you want to have? Three. One rotation doesn't make any sense unless you have two reference frames. Something is rotating if there is an observer that is looking at that object and can tell that it's rotating. It's relative, right? Rotation is between two objects, two reference frames. So one rotation is default, you have two reference frames. And then if you add more, every rotation you add, every single axis rotation is definitely another reference frame. So you know already by just looking at this drawing that you need three reference frames. Now what are those? Well, one is the ground, of course, G ground. Now if I go from the ground up, first rotation as is this rotation about the vertical axis. So you can use this shaft as the reference frame, as the second reference frame, which let's call it A if you like. But what it basically is if you think about it, it's like taking the ground and just making it rotate about the vertical axis, right? That's what it is. So you can say that is the first shaft. But that's really what it is. The ground that is, all the points of the ground, you just allow them to rotate. That's the second reference frame. And then it's called B, the third one. It's, of course, this second arm. B is, or second shaft, whatever you want to call it. OK. So we agree we need 3, and those are probably good ones. I don't want you in problems to tell me what are exactly the 3 points that define a reference frame, but ground, you can pick any 3 points that have fixed distance among each other. Here, you can imagine 3 points, and the same for the second bar. Coordinate systems. Now, with this, we need to be careful. You have reference frames. First thing you do is, I'm building coordinate systems now. What is the first step you do? Pick an origin. So, doing ground, which one do you want to pick? There is no unique answer to these questions usually. There is only you picking the one that will be more useful. You can pick Q. You can pick O as well, right? I want to say origin at O. Doesn't make a difference, to be honest. But I'm getting the feeling that there may be another coordinate system at some point that will have, actually the other two, that will probably have the same origin. Think about that point O. That point O is fixed in the ground, is fixed in A, and it's fixed in B. So it's probably a good idea to pick that. Q is fixed in A and ground, is not fixed in B. Right? So, OK. What else do you want to pick? This is the ground. The coordinate system needs a basis. What do we pick? This is where you need to be specific, telling me which vectors you decided to pick. You probably want to do an axis like this, right, in this direction, another axis like this, and one sticking out of the page, for example. But you need to be spelling that out. How do you define those axes? So they say that you have a first axis EX, and you want it to be in this direction. The horizontal and vertical here doesn't make any sense. I don't even have gravity or any forces, but that's just called this direction vertical. How do I define that? Okay, EX along OP when phi and theta are 0. Assuming that, of course, I'm assuming theta, I can see that brings OP down to this direction. Phi, I am assuming that phi is 0 when you guys look at this picture and you can clearly see the bar contained in the board, right? That's basically what we're saying. Does it make sense? As phi changes, that bar will go inside the board and then come out again and then go inside again. So I'm assuming that phi equals 0 means that you can completely see basically QOP contained in the board where I'm writing. So along OP, when theta and phi are 0. That makes sense? So that means that I'm locking this direction on the board, if you like, and then those frames, A and B, they can rotate as much as they want. That direction is not going to change. Then probably you want to do easy out of page or out of board. Just to be completely thorough here, you can say again that phi is 0. So that is coming out and it's not changing anymore as the two objects rotate. And then EY, these are all vectors, I'm sorry. Make sense? Okay, so that's the ground. Then we do A. As we said, O is probably good for everybody here. Origin at O. Now, I need to define a coordinate system, a basis that actually goes with the phi rotation. It goes with that motion, right? So what is the common axis here? Remember, every rotation involves that your coordinates, that you have two coordinate systems that probably have an axis in common, right? Which one is common here? Are you sure? I'm looking, forget about phi. I'm sorry, forget about theta. I'm looking at, so this piece is not what I'm concerned about right now. I'm just looking at this vertical shaft that is rotating about the vertical axis. So I need to paint three vectors in A. They go with A, and A is doing this, EY. So I probably want to pick let's call it little EY to be big EY. Okay. What else? I want to say a little EX along OP when theta equals 0. Only theta. I don't care about phi. Because now I am hugging that shaft A and I'm rotating with the shaft A. So I need to see unit vectors that don't change if I am attached to A. So it doesn't matter what phi is. That thing can rotate back and forth. So when I say that EX is the direction along OP when theta is 0, that is a very well-defined direction. Phi can be anything. So this remains attached to A, fixed in A. Make sense? Okay. And then what is EZ? What is EZ? EX cross EY. This is the most important part of the problems that you're going to face. This is the part where you need to spend time and make sure that you're doing it right, because these are building up, these are tools that will allow you to solve the problem. Without these, there's no point in starting to write down vectors and taking derivatives. There's really no point if you don't do this right. If you don't define reference frames and coordinate systems that are fixed in those reference frames, you really are going to have a lot of problems. So this is A, and then B is probably the easiest actually, right? I'll do it down here. GB, same story, origin at O. What do you want to use? Remember, define three vectors that go with B. They stay with B. So as we've probably seen before, I would like to do, I can call it UR, why not? Or call it UX, just change names. UX along, it doesn't really matter what you call these things, as long as you respect the fact that they are orthonormal and a right-handed basis. You can call them ABC, whatever makes it easier for you. So UX along OP. That's it. I don't need to say anything else. Theta and phi can be anything. It goes with the second shaft. And I'll let you pick this one. I've said this a few times. Every rotation involves that there is something that we copy from the previous coordinate system, right? So what do I carry from that one? EZ, right? So let's say that I have a UZ, which is corresponding to EZ, and then UY is going to be U. What do we do? UZ cross EX cross UX. Should speed this up a little bit. So good habit is also drawing a few things. Let's see. I know that for the last two, I have little ex is here, little ey is up here, and then in that same plane, I see ux and uy, right? Do we agree with that? Okay. And then probably the other plane that makes sense is the one that contains big EX, the ground. Let's see, this is EY, so big EZ. And then I probably see something like this, EX, EY, and this is the angle phi. I'm sorry, this is EZ, right? Make sense? So these help you in case you need to do some projections, which in this case you probably need to. The angular velocity of this B with respect to the ground will be the angular velocity of B with respect to A plus the angular velocity of A with respect to the ground. So you will have to do that. Again, I'm not going to complete this one. I really invite you to do it yourself. But this is the part that is the most time-consuming and brain cells consuming, setting this up. After that, doing those derivatives should be relatively simple with the transport theorem. Not easy, but simpler than just staring at the problem and try to visualize everything in 3D at once. You do it step by step. Define reference frame coordinate systems, do 2D drawings or how the coordinate systems relate to each other. That helps you understanding the geometry. This good? Those who've tried kind of got the same results up to this point? Okay. So let's do something else. Can I erase? We're all fine with this? Let's attack the one I gave you. And again, you may have tried already to do it by yourself. Last time, the two bars, two lines as far as we're concerned now. Nothing has a mass so far. So we don't really care about masses of bars or points. We just want velocities and accelerations. Let me see what I have here. Okay. Theta 1 is the angle with respect to the ground for this first bar of length L1. This is length L2. Point P is attached to the second one. It's not translating on the second bar. It's the edge of the second bar. And then we measure the angle between the two as theta 2. I called O this point here, the first hinge point, and the second between the two bars is Q. Slender uniform rods, that's it. So I want the usual suspects. I want the velocity of Q with respect to the ground, the acceleration of Q with respect to the ground, and then the same for P. Ground, acceleration of P with respect to ground. And we have demonstrated last time that you have that very long formula with the Coriolis acceleration, Euler acceleration, centripetal acceleration that you can use. But, and after at home, you can try to actually solve it that way. but you don't really need to memorize that formula, and you don't need to figure out what goes inside those vectors, because I think it will take even more time and will give you no insight with regards to the problem, because nothing will take away the fact that you need to define reference frames and coordinate systems anyways. You still have to do that, even if you want to use the formula. And once you've done that, it really doesn't make sense to use a prepared recipe that can lead to a lot of errors, actually. And so I would start with Q, right? Okay, let's see. What is well, actually, before I start with anything, what do? It's the same song here. What are the references? How many do I need? 3, 2 rotations. So probably it's a good idea to define G as one of them, which is the ground. And then I have the first, which is, I just call it bar 1. And then the second, bar 2. And then for those reference frames, I need to define coordinate systems. Ground, origin at O. I want to say EX along, what is that? OQ at theta 1 equals 0. EZ is out of page, and EY is the cross product of these two. EX, you start understanding here that there's going to be probably 3 vectors of 3 different coordinate systems that are going to be the same, right? There are 2 rotations, but they are about the same axis here, which is the one sticking out of the page. So it really doesn't help me drawing too many things other than what happens in the plane of the board. So EX and EY are this way, and these are my first 2 vectors, unit vectors. Then I move to A. What do you want to use for A as origin? O? Is it fixed in A? It's fixed in A. That's fine. And then I want to say little EX is along OQ. Fine. At any theta, of course, it's always along OQ. And then the rotation, guess what, is about the vertical, the z-axis. So I recycled the z-axis. Little ez is big Ez, and little ey is little ez crossed with ex, with little ex. Right? Okay, so let's add that to the picture. Little ex and little ey, and the rotation is theta 1. Good. Finally, B, you do that.
Ex around OQ, isn't it at theta 2 equals 0, or is it not a necessary condition?
No, I'm focusing, every time I look at the reference frame and I decide which coordinate system I want to use in that reference frame, I only look at that particular reference frame, that object. What happens around it, I don't care. It needs to be something built inside that frame that has a point that never moves in that frame, it's fixed in that frame, and 3 unit vectors that are orthonormal, right-handed oriented, that are also fixed in the reference frame. Whatever happens outside, I don't care. Does it make sense? So it's like grabbing an object and drawing lines on the object. That's exactly what I do. This is my reference frame. I start drawing lines on the table.
Yeah.
Pick a point.
What he might have meant is when theta is 0, then these 2 coordinate systems would be the same.
Yeah, of course. Yeah, yeah, they are the same. Yeah, at theta equals 0. Yeah. Origin at O. Yeah. Yeah, absolutely. I mean, in every problem that we'll see, it doesn't matter how many rotations you have. Between 2 coordinate systems, when an angle is 0, you will see reference frames aligning with each other. Yeah. Yeah. So for B, what do you want to do? Why do you pick the origin of Q? It's fixed in B. You can't pick O. At Q, and then I'm probably going to do the same that I've done here. What do I want to call this? UX, I guess. I'm out of symbols. UX, little UX, is along QP. And guess what? The rotation is the same, about the same axis. So little uz is little ez. And then the last one is little uy, which is little uz cross ux. And so I have ux, rotation theta 2, uy, so this is also theta 1, theta 2, and I'm lucky in this case that I have 3 of these vectors that are just the same. Those are more coordinate systems. Well, remember the unit vectors of a basis are free vectors. So I'm moving them to have the same point of application. They don't really need a point of application. So this is not O or Q. I'm just drawing these to understand how they're oriented with respect to each other. But remember, they have different origins. The coordinate systems have different origins. I am measuring distances from O if I'm attached to A. I'm measuring distances from Q if I'm attached to B. Okay? Good. Okay, so now I can start thinking about velocities and accelerations. And I want to start from Q probably. Velocity of Q in G is d dt in G of R. For now I can say Q with respect to O, and I'm going to drop this notation Q with respect to O. I'm just going to say R of Q. What is R of Q? ddt in G RQ. I'm just going to call it RQ. RQ is easy to write if I want to use the transport theorem. Of course, in this case, you don't see a lot of difference. This is one of the first examples we've seen where if you just go directly to the ground's reference coordinate system, you will start seeing sines and cosines. So when you take the first time derivative, you have sines and cosines. When you take the second, it becomes a little more complicated. So I really want to use the transport theorem, even in this simple case. So that means that I'm going to write Q in the coordinate system of A, attached to A. So that is L1 EX, little ex. Is that what I have? So this is the vector RQ expressed in the coordinate system fixed in A. And so if I use that, it means that I have to use the transport theorem. So d dt of RQ in A plus omega A G cross with RQ, which is equal to, should be able to do this quicker than what we usually do. So what is the first term? 0. Plus, what is omega AG? Okay, so this gives me L1 theta 1 dot. What is EZ cross with the X? EY. Okay. Then I do the acceleration of Q with respect to the ground, which is, don't skip writing it, d dt in G of vq in g with the transport theorem is d dt. See, I have the velocity of q in g as seen by an observer in g, but it is expressed in a coordinate system fixed in a. So it makes sense for me to just use the transport theorem again, right? d dt in a of vq g, this is a vector, plus omega a g cross with vq in g. You can stop me anytime. If any of the steps don't make sense, this is the time to stop me. Okay, so first rate of change. This is how this vector changes as seen by an observer fixed in A. This is a vector. If I am fixed in A, the only thing that I see changing is which of those mix of that's scalars and vectors, right, that I'm looking at. This is a scalar. The length doesn't change. This changes. Does this change in A? Doesn't change. So L1 theta 1 double dot little ey plus omega is the same, theta 1 dot little ez cross with v of q in g, L1 theta 1 dot little ey. What is this? Well, first remains the same, L1 theta 1 double dot little ey, and then I have L1 theta 1 dot squared ez cross with ey minus ex. So that's why I should usually wait before I put any signs in front of any cross product I'm computing. And that's the acceleration of q as seen by an observer fixed to the ground. Do they make sense dimensionally? Yes, this does. Length divided time, that's fine. Length divided time squared. This is radians over second squared. Yeah, that's fine. This is fine. Does it geometrically make sense? If I lock theta 1 in place, that doesn't change. First term, well, this goes to 0. If I lock theta 1 in place, well, the bar OQ is not moving with respect to the ground, so there's no velocity of q. And so these also will go to 0. Makes sense. Now, this is a case where the second reference frame, the third actually in this case, B, is rotating and translating. Q is moving with respect to the ground, right? So they don't share the same origin, A and B. So this is what we do. You can write this down, and actually I'm not going to need them anymore, except you need to know that you need to add them to something else. Okay, so the position of P with respect to O, and again I'm going to drop this with respect to O in a second, is what? Position of Q with respect to O plus the position of P with respect to Q. And let me just drop this, okay? We know we measuring everything with respect to O. That's our first reference frame. Well, then if I compute the velocity, v of P with respect to the ground is d dt in g of Rp, which is d dt in g of Rq plus Rp with respect to Q. Taking derivative is a linear operation, so you can do this. Rq plus d dt in g of Rp with respect to Q. I've done this before. I've just done it. So that's Vq with respect to the ground. I have that, so I erased it, but I have it somewhere. The second is nothing else than V of P with respect to Q as seen by an observer fixed to the ground. Same goes for the acceleration of P. And this is nothing different than what I've done last time to demonstrate that long formula. It's just that my suggestion is do it basically every time by yourself. Don't just look at the final result and stick in vectors. Just do it by yourself because it's actually easier. So AP is the derivative of, with respect to the ground, ddt with respect to ground, Vp in G. But there is also d dt in G of that expression, Vq in G plus Vp with respect to Q in G. Can split this in two pieces, d dt in G of Vq in G plus d dt in G of Vp with respect to Q in G. And likewise, I've done this. This is acceleration of Q with respect to the ground. I have it somewhere. And this is the acceleration of P with respect to Q as seen by an observer fixed to the ground. So the procedure is you work your way through the reference frames. You have computed what happens to the point Q, which is the origin of the next reference frame, or save that on the side. You basically need to compute what happens as seen by an observer fixed to the ground with respect to that point. That's what these things are. This is the velocity of P with respect to Q as seen by someone who's sitting on the ground. And this is acceleration of P with respect to Q as seen by someone sitting on the ground. So I have to compute these and these. That's it. And then I add it to what I had before. OK, so let's start with this one. ddt in G of RPQ. How do you write R with respect to Q? RP with respect to Q? I think we can just go here. Well, I think it's easy to do the following. Probably is just L2 UX. So guess what I'm going to do? I'm just going to do the transport theorem again. Nothing special. Just do it step by step. When you have multiple reference frames and rotations, go to each point, each origin of the next reference frame, compute that, and then move on. OK, so if this is the way I can write RPQ, then I'll do the following. This is d dt now with respect to which reference frame, if I want to use the transport theorem. And I'm in B, d dt in B of Rp with respect to Q plus omega B ground cross with RPQ. This is really no-brainer, right? This is 0. Make sense? I know that. If I'm sitting in B, I don't see the point P doing anything, as it is part of B. It's fixed in B. OK, I need to figure out only this term now, omega of B with respect to the ground. What is that? This is a very simple case. You add them up. So this can be broken into omega of B with respect to A, right? Remember the little trick, whatever you want to call it. I'm going from B to ground. So I do intermediate step. I go first to A, and then from A I go to ground. I know how to write these two because this is theta 2 dot u z. Is it z? Yeah. Make sense? That's the angular velocity of the reference frame B as seen by an observer in A. So I am now sitting on A, and I see this second shaft moving according to an angle theta. So that's all I see. That's its angular velocity. And these, we've done it before. This is theta 1 dot. Well, they're all the same. I can write, just to be consistent with A, I can write little ez if you like. But little ez and uz are the same thing. So this is really ends up being theta 1 dot plus theta 2 dot. So let me use the u coordinate system. Little uz cross with L2 ux. So is this giving me? This is giving me theta 1 dot plus theta 2 dot L2 uz cross Ex, this is a minus, right? No? Yes? Positive? Your positive is positive? It is positive. Okay. So if you want to go back and tell me what is the velocity of P as seen by an observer fixed to the ground, you add this to the velocity of Q as seen by an observer fixed to the ground. You're done with the velocity. Questions? If you break the problems down into pieces, they're so much nicer. It doesn't matter how complicated they are at the beginning. Once you figure out the reference frames, the coordinate systems, they don't look like monsters anymore. Okay, so then I have to do the derivative of, remember this was Vp with respect to Q as seen by an observer fixed to the ground. So I take the derivative of this now. D dt, keep skipping steps. Let me write what it is. AP with respect to Q in the ground is d dt in G of Vp with respect to Q ground. Guess what I have? I have that vector that I'm trying to derivate expressed in a coordinate system which is fixed in B. So it makes sense to use the transport theorem again. There's nothing new here. So d dt in B, Vp with respect to Q, as seen by an observer fixed in G, plus omega B ground cross with the same vector. Okay. What is the first piece? From now on, you tell me what to do. And the next problems we'll do. This is 0?
No, it's not 0. It's theta 1 double prime plus theta 2 double prime.
So if I'm fixed in B, that is the vector I need to compute the rate of change of. And I am fixed in B. Those angles keep changing. They're scalars. Remember, derivatives of scalars do not care about in which reference frame you are. If they're changing, they change in the same way. Scalars do that. Vectors don't. They depend on the frame. So even though u little uy does not change in B, L2 does not change in general. Theta 1 and theta 2 change, so they change. And so that, you have to have it there. Theta 2, theta 1 double dot, plus theta 2 double dot, L2 uy plus, we just computed the angular velocity. What was it? Theta 1 dot plus theta 2 dot, little uz cross with that again. Okay. Let's do this. What is uz cross with uy? Minus ux. Yeah, okay. So I'm left with theta 1 double dot plus theta 2 double dot L2 uy. We said minus. Okay. Then I have theta 1 dot plus theta 2 dot all squared L2 ux. And I'm done. So you add the velocity of p with respect to q as seen by an observer fixed to the ground to the velocity of q as seen by an observer fixed to the ground, and that gives you your v of p. You want me to write it down again? We just computed that before. We finished computing these. You just have to add them together. Acceleration p with respect to ground is same story. We had this before. Acceleration of q with respect to the ground. You add what we just finished computing. And that's what I invite you to do for all problems. When the reference frames don't have the same origin, they don't share a point that is fixed in both reference frames. Does it make sense? We have a couple more minutes. Do you have any questions so far? Yeah.
Here we have 2 rotations, so we took 3 reference frames. If we have infinitely many, like say 10, and we have to take 11 reference frames, and then the calculation becomes very cumbersome. So is there any better way to do it? Because
I would never give you a problem with 10 reference frames. It's crazy.
No, because I was just thinking we are on Earth,
Yep.
and there are satellites moving with us, and there are planets also, and there is like
Yep.
I was just reading how to find out the distance between the Earth and the Sun.
Right.
So we have to take about the Venus, think about the Venus and the Mercury.
Right.
So in that we have to take 3 rotations and revolutions, and then we have to take very long calculations.
Right.
In that case, if we do this, it becomes almost impossible because we will be making many errors.
How would you do it?
That's what I was thinking.
Well, if you have many rotations, first of all, between 2 reference frames, that's my suggestion. It doesn't matter how many reference frames you have, you build your way up. So you just focus on 2 of them at the same time, not all of them together, which is that final formula I gave you is actually doing. That formula I gave you that we derived the last time will give you directly this velocity and acceleration of this point. You have to plug in all the angular velocities correctly, the angular accelerations correctly. I didn't compute any angular acceleration here directly. I mean, I see it because I have a theta double dot, but I haven't really bothered computing the vector. So if you use the transport theorem from a frame to the next one, and then to the next one, then to the next, it doesn't matter how many you have, you just focus on 2 at the time. Does it make sense? Between 2 frames, the most that you can see is 3 rotations. We'll see all the angles. So, but between 2 given frames, the orientation of a frame with respect to another, at the most is represented by 3 angles. You can't have more than that. So you can have this is a spherical joint and this is a spherical joint. That becomes more complicated, but you still focus on 2 reference frames at a time, not all together. So even if this was a spherical joint, well, then you would have to tell me what is the angular velocity of A with respect to the ground. And in that case, if it's a full 3D rotation, we will derivate this. There is an expression that tells you how to write the angular velocity as a function of the rate of change of 3 Euler angles, which is an ugly matrix that multiplies the derivatives of the angles. There's nothing better you can do. But that is also broken down into single axis rotation. So that's how we will build it. So yes, between 2 frames, the worst you can get is that the rotation is full 3D, and then you have to do it you have to represent the angular velocity as a matrix that multiplies the rate of change of 3 angles. That's the worst you should see. But again, I don't advise trying to go, if between ground and your final point that you want to focus on, there are 10,000 reference frames. Yeah, this may take a long time, but you still have to, with the other formula we derived, you still have to figure out what is the angular velocity of your final reference frame with respect to the original one. So then no one will take away that from you. If the reference frames are in between are moving in all sorts of ways and they're all spherical joints, well, that becomes multi-body dynamics. And that is actually done in most of the cases numerically, yeah. It can get complicated, yes. Any other questions? Okay, so we'll do another problem with reference frames that have not a shared origin next time, which is a little more complicated. And then we'll move on to new topics. Okay, thanks.